Hi everyone, thank you so much for coming to my session, and I'm so excited to share with you what we have been building in the last couple of years, and hopefully can get feedback from everyone here. So let me start from kind of something that I hope everyone can kind of like agree like at this moment, that is actually machine learning and AI has been making this fascinating progress over the last couple of years. We now see machine learning application pretty much everywhere, from small things like smart sensor to your smartphone to something bigger as a smart city, something like that. So on the other hand, the demand of machine learning and artificial intelligence is also there, rapidly increasing. So at ETH Zurich, we are so lucky and privileged to have been working with a whole bunch of people who are trying to use machine learning to revolutionize their field. Like even for my kind of small research group, we are kind of lucky to work with together with a whole bunch of people across so many different departments, and also our friends in both public and private sector, dealing with defense, finance, healthcare, so on and so forth. So if you look at these two different group of people side by side, right? So one observation that we had over the years kind of surprised us in the beginning, that even these top people in their specific field and these leaders in their industry also need help in applying machine learning and AI to their field. If this is true, it actually begs the question that what about other people? What about smaller companies, right? So how can we make sure that everyone in our society can all benefit from machine learning and artificial intelligence to really face the challenge of the future? So our way to really try to understand this question is really try to understand what is really stopping us from putting the latest AI technology into the hands of everyone. So of course, a question like this is never pure technological, because there are so many different angles to this question. Some of them are educational, right? We should continue to keep our universities strong to produce the next generation of leaders and engineers, right? Some of them are social economical, some of them are related to regulation. But nevertheless, I would argue technology is still at least one of the foundation. And if you look at the technology, among many of those factors, so what we have been thinking about and looking at is the cost. Because that's a question that people keep asking for any new technology when people try to democratize that to replace an old one. So we had this 100 years ago when we think about cars, because think about how cars are being put in the hand of everyone. In the very beginning, 400 years ago, right, we kind of know a little bit about what to build, right? We started to build that over the years, but not until we have this fascinating Model T from Ford that really decreased the cost. It is the time we start to put that technology into the hands of everyone. So if you look at machine learning and artificial intelligence technology today, what we argue is building that technology is actually very, very expensive. And that's one of the key reasons that you do not see that being applied to every single applications nowadays. So what you directly need is actually the Model T of AI. And that is actually something that my research group is really trying to understand. So, but it's a very hard problem to look at, because machine learning and AI can be really expensive in so many different ways. For some of those models, they are simply very expensive to train, right? If you look at GPT-3, those big language model, well, and simply need like a lot of computation. If you look at those state-of-the-art recommendation models, and they simply need a lot of memory to actually hold those models. And together with the ownership cost of the infrastructure, right, it's very kind of common for you to spend millions of dollars to just train such a language model, or just spend, for example, $20,000 per day to just hold that big recommendation model into your memory. And this is just about a single model, right? When you go to development, right? So you need someone to actually build that application. That could be very expensive. And also machine learning is always fun about the data itself, right? Sometimes the annotation and the cleaning itself of the data could also be very expensive. And also people start to worry about things not only about accuracy, but also fairness or robustness. They start to have compliance costs to different type of regulations, and not to say the operational costs about monitoring, testing, adapt, and really scale up your deployment of your machine learning application. So if you look at this, like all those costs, so they're actually very expensive. The goal of our research group is really try to understand how can we bring down all those costs by at least 10 times. So we hope to turn what used to take 1 hour to something that take 6 minutes, what used to take 10 label to do to something that you can do with 1 label. So our central hypothesis is once those costs are being brought down significantly, it will actually change how we are developing and testing those machine learning models today, and make many of those hard social, economical, and regulatory problems or discussions much easier to have. So, but this is super hard problem. So specifically, we have been working on this like 2 different questions. So for the first question, we look at the training of a single machine learning model, and we essentially take every single bit you need to communicate through the network, every floating point operation that you need to do, every synchronization barriers that you are enforcing, that the machine wait for each other, every data movement and shuffling you are conducting, every piece of data you must hold in memory, every single fast connection you are building between those devices and machines, essentially everything that is making machine learning training expensive, and try to ask, are they really necessary? Right? If they are not necessary, how can we design a new algorithm to accommodate that? If they are really necessary, how can we build the next generation of machines to make them easier to run? So second thing that we have been looking at is by looking at the process of improving the quality, not only for accuracy, but also for fairness and robustness of a single machine learning model, continuous testing the quality of machine learning model, adapt the machine learning model to different scenarios. And we look at those processes and try to ask, how can we make them as systematic and data efficient as possible? So it turns out we can actually get a positive answer to both of these questions. So in terms of training a single model, so what we realize, yeah, so not all of those things that making machine learning training expensive are really that necessary. If you co-design the algorithms, the data ecosystem, and hardware, this can give you at least 10 times in many of those applications. So this is not only theory, right? And you can also play with the thing that we have been building over the years. If you're using PyTorch Lightning, like training your machine learning model today, you can actually turn on the thing that we have been building with a single lines of code with a trainer called Bagua, can give you a whole bunch of system relaxations for machine learning training. If you are like training machine learning model inside database, if you're using OpenGauss, you can also try to use some of the things that we have been building over the years. So in terms of the second question about the processes, right, what we realize is many of the steps of building machine applications can be made systematic, and there's at least 10 times to save if you give the guideline to your user to have more targeted attention to many of those tasks. So the thing that we have been working on over the years is this end-to-end process, all the way from data injection, augmentation, to cleaning, to acquisition, and also to testing and optimization, this end-to-end DevOps process for machine learning. So the thing that we have been I will talk about today is actually focused on a very small components of this picture, and I will show you the functionality that we have been building over the years, and also how does it touch the 3 different type of cost, both computation, the development, and the compliance cost of machine learning. So more technically, the thing that I'd like to talk about today is actually how to jointly reason about data quality and machine learning quality. So if you think about how machine learning applications are being built today, if you worry about a single machine learning model, it's actually not that hard to build, right? You can take any of your favorite cloud service provider, and they all give you some AutoML functionality. And once you have that, building machine learning applications become kind of easy, right? So in Switzerland, we have this fascinating data system called Rinko, right? So we start to integrate some of the things that we have been working on there. But the process is the same, right? If you want to train a single machine learning model, all you need to do is, okay, I have a whole bunch of data set, right? So I import that data set into whatever system that you want to do, right? And then with a single lines of code, right, or single click of the button, you can actually start a train of multiple models, and at the end of the day, you get some model, right? So in this example, as you can see, just after a couple minutes, right, you get a model with, yeah, not a bad score. But what's next? And that's a question that really interests us, because what if this model is not good enough, right? What should we do? And what's the reason that this model is not good enough? And if we want to fix it, what is the most important thing for us to actually fix? So if you look at those, there are actually a whole bunch of problems. So this is a textbook picture about how machine learning models are being trained today, right? So you on one hand, you have training data, contains a whole bunch of examples with a whole bunch of labels. You pipe that through your machine learning training process, you get a machine learning model, and you can measure a whole bunch of quality for this model. there's accuracy, there's fairness, but there's something that you can actually measure. So of course, the model itself has a very big influence to all those kind of model quality dimensions. But on the other hand, your data could also have problems. There could be missing value, there could be wrong value, and there could be millions of those data examples. Traditionally, in data management, we have these 4 different dimensions of data quality. And intuitively, you can see how these 2 different dimensions kind of map to each other. If your data have low accuracy, then maybe your model could also have low accuracy because you are learning from a piece of data that have noise. When your data quality have completeness issues, your model could have fairness issues because you are missing potentially a very big chunk of your population. So, and this is actually one thing that we have been doing over the years. Like back in 2019, we have this very simple experiment, right? So essentially, when you have a very dirty data set, you could try to run a whole bunch of machine learning models, and as you can see, those machine learning models do have different quality, right? But magically, they all stop essentially at this magic number 76% F1. But this is essentially what your data set can actually support. But once you clean your actual data set, fix a whole bunch of data problems, right? Even a very simple machine learning model can give you this dramatically improved F1 without changing anything on the machine learning side, but just changing the whole thing on the data side. So from this, essentially, often if you look at what happens in practice, the best way to actually improve your machine learning model is actually often to improve your data. But this is actually, unfortunately, something that's easy to say, but kind of harder to do, because there are so many problems that we could have where you can take this picture and ask user to say, okay, fix your data to make machine learning better. So first one, there could be so many things that you could do, right? You could get more features, you could remove outliers, you could get more data example, clean your data example. So first struggle that we see that people are facing today is that they could be overwhelmed by the amount of possible operations that could do on their data set. And second struggle is actually not all those operations are equally beneficial, because maybe there's only a very small component of this data problem are actually the root cause of your machine learning model's low quality. You need to find all those small components within these millions or billions of possible ways that you can actually improve your data set. And what makes things even worse is that after you fix your data, the feedback loop could be very, very slow, because you could wait 10 minutes or 1 hour for the machine learning model to train, and then you know whether your fix actually makes sense or not. And fourth struggle that we see our user often face in the practice is real-world machine learning is not always about a single machine learning black box. So often people are dealing with a piece of code that looks like this, that only small components of that is about machine learning training, but a very large components is actually about data transformation or feature extraction. So if you put these 4 different struggles together, what we observe in practice is many of our users are actually wasting their time and money fixing data problems that often do not really matter at all, and the worst, they're actually missing those really important ones. So our user need help, and help that we actually try to provide to our user. Before I talk about the technical side, so let's imagine an ideal world, what we actually want from the system. So wouldn't that be nice if you have a magical system that every single time you write a Jupyter notebook to build your machine learning application, there's a magic box there called debug for accuracy or for fairness, and once you click that button, we highlight all the potential problems of your code that making your machine learning model low quality, unfair, or not robust. And if you do not want to write code at all, wouldn't that be nice that every single AutoML system have this magic button called improve your data, and once you have done that, right, so we show you all the potential data examples that can cause in the problem of the low quality of your machine learning model. So these are the 2 things that we really hope to build. But they are actually hard problems to tackle to actually make this happen. So from a technical perspective, the thing that we have been looking at is this end-to-end machine learning pipeline. On one hand, you have machine learning models, so you have data with a whole bunch of data problems. you pipe that into your feature extraction pipeline, train your machine learning model, get your machine learning model, and then you measure certain notion of utility of this model. And then the thing that we kind of want to understand is to assign certain notion of importance for both the data example, but also each feature of extraction operators in this pipeline to identify their importance to my machine learning utility. So there are three different technical problems here. The first one is actually how to define those importance. It's actually very challenging because you are actually trying to compress a complex problem into this single dimensional number, could be very hard to define. And second is how can you really enable real-time interactions. We want to make sure every single time user fix something, the feedback loop can be as fast as possible, and ideally real-time in the sense that less than a single second, we give back that signal. And third question is actually how can we use that? So let's go through these three different questions one by one in this talk. So how can we define importance? So this is actually not a simple question to answer. So let's just look at one example. I have these 4 different training examples, right? So, and I want to understand, okay, what is the importance of this red tuple? So how can we think about this? Well, I mean, one way to think about that is to do some intervention on this data set, right? We could say, okay, now let's measure the accuracy on the whole data set, and then let's try to remove this red tuple, and then we can measure some notion of improvement, right, by removing this tuple. So this can already give you actually a lot of information about how important this red tuple is. But unfortunately, it could also be suboptimal. And it's actually not that hard for you to find an example to actually see why this leave one out notion of importance is not optimal. So let's just imagine this application. You have these 4 different examples. 2 of them are bad examples and 2 of them are good examples, right? And your utility is formed in a way that as long as you have a bad example, you have very low utility. Once, like only if you have all those examples that are good in your data set, you have this very good utility. If you take this view, and let's try to compute the importance, this leave one out notion of importance for this bad red tuple, right? In this case, right, if you remove it, right, you still have one bad tuple inside your data set, so your improvement or your importance, right, could be 0. If you compute this importance for this good tuple, again, you could have 0 there. So as you can see, this leave one out notion of importance could be very confusing to users, especially when there are correlations between those examples, which is often the case in the practice. So we have to do more, right? So one way to actually do better is not only to consider this a single data set, but instead consider this exponential many different ways you can arrange the rest of tuples. And for each of those data sets, you add back this red tuple and consider these improvements. And then you try to aggregate all those improvements in a certain way and use that as your importance measure. There are so many different things you could do when you aggregate those. You can actually aggregate all those improvements using uniform weight, right? In this thing, like in this way, you have something that's closely related to something called multilinear extension, right? It actually works well to many applications. You can actually try to aggregate them in certain specific way. You get something called Sharpe value, have very sound game theoretical foundation, many good properties, and works well in practice. So essentially in practice, right, if you look at these 3 different ways of measuring in practice, there's actually a very interesting trade-off. So I wouldn't go to detail about the trade-off, but essentially in practice, you might want to use either the uniform weight or Sharpe value. Sometimes they actually outperform this leave one out notion of importance. And that's actually something you can see in practice, right? So this is one application that we try to debug every single feature extractor in the machine learning application, right? So, and then what we do is here, the x-axis is actually how many operators that we change, right? We just go through all those operators with the lowest value or importance, right? And try to change them into a better alternative. So, and then the y-axis is actually the accuracy improvement of this machine learning application up to fix some of those operators. So as you can see, if you only change one operator, leave one out almost by definition is the best, because that's actually try to change the operator that actually going to increase your accuracy as much as possible. On the other hand, the uniform weighting and the Shapley value, yeah, I mean, slightly worse, do not give you too much. But once you actually start to change more than one operators, you see this very significant gap between leave one out and uniform or Shapley weighting, right? So that is actually the improvement that you get by considering the correlation between all those operators. So it actually make a very big difference to actually consider many possible improvements. But as you can see, it's actually couldn't make your computation super expensive to do. And you can also define importance not at the tuple level, but also at the cell level, right? So imagine you have a one training set that is actually noisy, right? In the sense that for every single cell, right, you have uncertainty on your feature. It could take different values. You train a machine learning model, you get some model, you get some accuracy, right? And we try to understand what's the impact of those dirty data to the final machine learning accuracy, because not all those dirty data actually matters equally. What is the importance of this cell? So there are many ways to think about that, but one way to think about that is actually by trying to look at the noise and try to expand this noisy data set into a whole bunch of possible worlds. Each one of them are without uncertainty, right? So they actually, you try to instantiate every single noisy cell, right, into a concrete value, and then you try to train a machine learning model and try to aggregate their feedback back to the user. If they all agree on certain prediction, you have your answer. If they agree on another prediction, you have your answer. If you disagree, you tell the user, okay, I don't know, right? You can also aggregate them in a softer way. You can have expectation or entropy, so on and so forth, right? If you take this view, right? So actually the importance of a single cell is actually how much you are expecting it to actually bring down your uncertainty, right? So every single time I clean a cell, I have a new prior on the noise model. You can actually measure your expected improvement by knowing that piece of information in a concrete way. So there's so many different ways to define the importance. So second thing that I'd like to talk about is actually how to compute those importance. So there are so many different challenges. That's actually two different challenges. The first one is that if you look at those importance that we have defined, the thing that actually works really well in practice, they are actually very expensive to actually compute. If you look at Shapley value and expected improvement, right? So given a data set with n different examples, we need to enumerate all the possible ways to arrange those tuples, right? And for each of those exponential many possible worlds, you need to train a single machine learning model and measure some accuracy or some fairness stuff. In terms of entropy or expected improvement, it's actually not getting easier, right? If you have a data set, right? So even with m different choices for every single cell, you are talking about this exponential many ways for you to instantiate the possible value for each of those cells, and for each of those ways you need to train a single machine learning model. So as you can see, this quickly becoming infeasible, so we have to do something about it. The second challenge is machine learning in practice doesn't often look like this, right? So often they actually look like something like this, where only a small component is about machine learning, but the vast majority piece of code that you're actually writing in practice is about feature extraction or data transformation. So we actually have no idea how to deal with these two components side by side. So from a theoretical perspective, we are lacking a fundamental understanding about how to connect the decades of study in two different areas. On one hand, the data management and database community try to understand data transformations, and on the other hand, there's a machine learning community try to understand the importance of data to machine learning models. We have to combine these two things in some way. So what do we know how to do? So once that we know how to do is, if you look at this end-to-end pipeline, it's actually super hard to analyze, but you are able to make some progress. So one thing I could do is to approximate this very complex pipeline into a proxy pipeline. You have a simpler noise model, you can approximate the feature extraction pipeline by only keeping the provenance. I will give you some example relatively soon. You can actually approximate this machine learning training process into some simpler machine learning models, for example, k-nearest neighbor classifier, and then you try to use this proxy pipeline to debug your original pipeline. So essentially it looks like something like this. On one hand, you have your end-to-end machine learning model, right? So, and then you try to transform them into these two different components. You try to approximate this feature extraction part into the traditional notion of data provenance. That is, how does it transform the data example? In the input, right, you have this x1 and x2, there's two different tuples, right? If whatever this feature extraction pipeline try to do is to transform x1 into another example, transform x2 into another example, you have this map-shake pipelines, one-to-one correspondence between input and output, right? The way to express it is they become some polynomial in the problem seminary, right? You have different shape. If you have, for example, data augmentation, right? One data example become multiple of those, right? You can have this one-to-many join to collect information from different places, right? There's a principal way if you talk about those feature extraction pipeline, about the provenance, and then you try to replace this machine learning pipeline into something simpler. So once you take this view, right? So surprisingly, one thing that we learned over the years is many of those like realistic pipelines, if you look at the proxy pipeline, you can actually compute a whole bunch of things, the entropy, the expected prediction, the sharp p-value in polynomial time. And the complexity of this is actually depends on the shape of your feature extraction pipeline. And this actually give you a huge improvement on the performance. In practice, we often see actually like 1,000 to 10,000 times speed up compared with a baseline solution doing Monte Carlo to actually approximating kind of those values. So second thing that actually we learn is actually it works, right, in many of the applications. So that brings us to the third question is actually how can we use those importance? So you can actually use them to debug your data. So but look, so here's one example. Assuming you have a data set with a whole bunch of label noise, right? So here, as you can see, the cat is labeled as dog, the fish is labeled as cat. You train a machine learning model and you say, yeah, the accuracy is actually not good enough. I have to do something about it. So one thing that you can do is actually you can actually follow the importance being computed by the system. For example, you compute the sharp value for every single data example, right? And you try to see, yeah, so I look at those negative ones, right? And try to understand whether we can fix their labels. So here the x-axis is a fraction of data that you inspect, and the y-axis is the accuracy of the end-to-end pipeline. So here we are using the XGBoost classifier, right, for this original pipeline, and we try to debug it. So you could do this randomly. There's nothing stop you from doing this randomly, right? So as you can see, if you just randomly pick example to fix, you are able to make progress. Don't get me wrong, right? So once you fix stuff, right, you have this improvement of your accuracy. The more you fix, the higher accuracy that you get. But if you follow this sharp value from the K-niche numeric classifier from the proxy pipeline, is a system called we call the data scope. As you can see, you can get this more dramatic improvement of your accuracy by fixing fewer amount of data. So here essentially you can fix 2 times fewer amount of data, but still achieving the same accuracy. And that is a saving that we could provide to our user. On the other hand, right, you can also do direct Monte Carlo, right, which in this example is 10 times, like 10,000 times slower, right? But still, yeah, so you are able to get pretty much the same accuracy improvement given the amount of data example you can fix. And this actually becomes more interesting when you consider different objectives. So here's another example. So we have one data set that if you clean 100%, it has some fairness issue, right? So in this case, if you look at accuracy, right? If you look at cleaning, if you can randomly clean it, you have better accuracy over time. You can also clean that like using data scope, right? So yeah, so far so good. But on the other hand, if you look at the unfairness of the system, right? If you randomly clean it, right? The more you clean, the more unfair your system become, because the 100% clean clean data could be unfair in this case. But you could also take our system and try to use unfairness or fairness as one of the objective. So if you do that, as you can see, you can actually maintain this high level of fairness until essentially 70% of the cleaning process. In the first 70% of cleaning process, right? So you can actually keep essentially the same fairness, right? At the end of the day, when you clean everything, it's out of our control because at some time you are going to reach that unfair point. But in the majority components of the cleaning process, it's actually fair, right? You can actually stop at 75% when you have a good accuracy and still maintain this fairness thing. So one thing that's actually interesting is if you look at this, right, by taking a more strategic view of data cleaning, you can actually have this 20 points better accuracy for your application, but on the other hand, maintain the same level of fairness, 5 to 10 points better than running strategy. So what about this baseline, this Monte Carlo baseline, right? In this case, this is actually one very interesting example that the faster speed of the system actually can translate into better development pattern, easier quality improvement. So because if you look at this Monte Carlo thing, right, because it's so slow, right, you can only run that once. But for Datascope, because it's so fast, you can actually keep running that every single time you actually fix some data example. So in this case, that is actually where this gap comes from. We can run our system for every single 1% of data set that we actually clean, right? Even though we are running this 100 times more than the Monte Carlo baseline, right? Aggregately, it's still 100 times faster than running that even once, right? So as you can see, here is actually make a difference, not only in speed, but also in quality. Because if you try to do data cleaning for fairness, the notion of importance will keep changing once you clean more of your data example. And you can also do this for data cleaning, right? So assuming you have one clean oracle on the feature side, right, to tell you, okay, so this is the right value for this feature, right? You could also try to prioritize your cleaning by trying to minimize your entropy as much as possible. If you do this, you can get a cleaning strategy that actually improve much faster than the random cleaning strategy. And this is something that you can already play with. The algorithm is being integrated into two different systems, right? So you're more than welcome to play with both of them and give us feedback. So here's actually just one example on the Datascope side. You can go to the Datascope website and you can see the Jupyter notebook. So what's actually interesting is actually very simple to use, right? You can give me your machine learning pipeline in scikit-learn, right? You do not need to change anything, just have that pipeline there, right? You try to input the utility function that you want to improve, and with a single line of code, right? You can actually get the importance of your training example. And once you have done that, you can actually follow your importance to try to clean up your data set. So please play with it and give us feedback. So today I talk about these very small components about data cleaning and data aggregation. But when machine learning and AI kind of moving toward this more data-centric like view, right? So there are so many different problems that we can actually work on, and really excited to get feedback from everyone and tell us, yeah, what are the hard problems that you want to see solved in the next couple years. So that's all I have for today, right? So again, like go to these three different websites if you're curious about our work. Again, thank you so much for your invitation and for your attention. I'm now happy to answer whatever question that you guys may have. Thank you.
Thank you so much, Thor, for that wonderful presentation. For our audience, if you have your question, please send in your question through the Q&A link that was sent to you, and Thor will be happy to answer them all. In the meantime, let me thank sincerely everyone who have joined us for this session. Please don't forget to fill out the survey which you will receive at the end of this session, because your responses to this survey help us to better plan our future conferences. Don't forget also to tell us those speakers that inspired you so much through your social media. And then you stand a chance to win an Apple TV and other cool prizes from our ODSC partner when you do that. Thank you for joining us for this session. Thank you.
Yeah, so how does the question answering work? So I see there are some questions on my side, but there's some errors in the chat functionality, I think they say.
Yes, I see that one person mentioned only that there was the error, so I'm not sure if it's from their side or from ours, because I checked and it worked well. just in case, if for someone doesn't work via the link that is shared, just go to agenda on the session from the chat, Zhang, and there is the Q&A link embedded. So just click on it and it will redirect. Maybe just because of you're not logged in, or maybe that's because of it's from external platform to external platform and doesn't allow on your laptop. Probably there is the issue, but everything should work. And there was the question about the prerequisites or slides where they can find. So I shared the prerequisite links, but yeah, Zhang, if you have something additional that you would like to share or any other materials that it's worth for attendees to have, feel free to share it in the chat or in the Q&A session link too.
Yeah, let me try to type. Yeah, essentially you can find those information in the GitHub that we have here, right? There's demo, there's code, right? So yeah, so play with it and give us feedback. We're really looking forward to actually hear from you about what you think about the system, and also where does it break, right? Where do you see we could do better, right? Yeah, and if you have other questions, just send me an email to follow up, right? Really looking forward to hear from you guys.